Welcome back to the fifth and final section of Chapter 8. In this section, we are going to be looking at linear, exponential, and quadratic models. In the last section, we looked at quadratic models. Previously in the year, we looked at linear and exponential models. So now we're going to be comparing them, seeing how we can tell which one will best model a situation, and things like that. Our learning targets for today: I can determine whether a linear, exponential, or quadratic function best models a data set. And so, how do we tell which model to use? Well, looking at a set of data, here we have a set of data. The very first thing we want to do is we want to look at those x values. We want to make sure that they're all going up by the same amount. So from -2 to -1, that's +1. From -1 to 0 is +1. From 0 to 1 is +1. From 1 to 2 is +1. That's very important for anything, because if the x values are just kind of scattered, then the y value, like, there's no pattern to find. Now, they don't always have to be going up by 1, but they have to be going up by the same amount each time. Once we have that, we're going to look at the y values. The first thing I would look at is how much do these ones go up by each time. From -1 to 1, that's +2. From 1 to 3 is +2. From 3 to 5 is +2. From 5 to 7 is +2. What do you notice about all those numbers? Hopefully, you're noticing that these are all the same. This is what's called a first difference. In fact, in this case, it's a common first difference. And what that tells us is that this is linear, because that first difference is the same. Not that there's a pattern in it, but those numbers are the same. Now, with that being said, when we get into real world situations, they might be really close, but not perfect. Just like I mentioned in the last one, we've got some variation that might go on where it won't perfectly fit the model, but it would still be a good model. But in this case, +2, +2, +2, +2, that's all the same. So that means it's linear. All right, well, let's look at this next one. So this next one, first thing to look at, these x values. Again, okay, those are, again, +1, +1, +1, +1. Okay, so now we can look at the y values. So let's check out those first differences again. So the first differences, to get from 3 to 9, that would be +6. It's called a difference because technically we're going 9 minus 3 is 6. 19 minus 9 is 10. 33 minus 19 is 14. And 51 minus 33 is 18. So you could do it with subtraction, or you could think, all right, so 3 plus what is 9? 9 plus what is 19? 19 plus what is 33? It's the same thing. So we have 6, 10, 14, and 18. So what we should notice here is that these are not all the same. Okay, well, what would we do there? We're going to find the second differences. What are the second differences? The second differences are just the differences of the first differences. So 6 to 10, or 10 minus 6, is 4. 14 minus 10 is 4. 18 minus 14 is 4. This is going to be a common second difference. And what that tells us is this is quadratic. Now remember, quadratic, we're looking at x squared something. That squared the second difference. Linear, we had x to the first for the first difference. If the second difference wasn't the same, and we found a third difference that was the same, it would be a cubic. It would be x cubed. That's beyond what we're doing right now, but this pattern actually extends. If we had enough data points and the 17th one was the same, we'd have an x to the 17th type of a function. I don't see that happening. I don't know if I've ever seen a model with that, but I'm just saying that that's how it would happen. So the first difference was linear. The second difference meant it was quadratic. If those were the same, well, how about the next one? So chances are this one's going to be exponential, being that we have linear, quadratic, and then exponential. But let's see what would make it exponential. So first of all, we have to check those x values. Make sure they're all going up by the same amount each time, which they are. All right, now let's look at our differences. So we have our first differences. So 1 to 2, that's 1, 2 to 4 is 2, 4 to 8 is 4, 8 to 16 is 8. All right, that didn't work. Second differences. 1 to 2 is 1, 2 to 4 is 2, 4 to 8 is 4. Wait, these are the same numbers. So we're not going to get anything other than 1, 2, 4, 8, 1, 2, 4, 8, 1, 2, 4, 8. So we're not going to look at the differences there. Instead of the differences, we're going to look at the ratios. So we're going to do a number divided by the one before it. So instead of subtracting, we're going to divide. So 2 over 1, 4 over 2, 8 over 4, 16 over 8. What do those equal? 2 over 1 is 2, 4 over 2 is 2, 8 over 4 is 2, 16 over 8 is 2. Hey, those were all the same. That's a common ratio. And we saw that back when we were looking at exponential functions. We were looking for that common ratio. That's the b value. We have a times b to the x. That's b. So if it has a common ratio, that makes it exponential. So what kind of order would we do this in? Oh, an exponential, remember, it was y equals a times r, that common ratio, to the x. So how would we find this? We would not start out looking to see if it's quadratic, because we go through linear first. Like if it's not linear, then we'd go to quadratic. If it's neither of those, we could go to exponential. But if you're looking, like I see, like, oh, hey, 1, 2, 4, 8, 16, hey, that's times 2 times 2 times 2 times 2, I'd probably start out with exponential. If it looks like, hey, this looks like it's always multiplying by the same amount, start with exponential. Otherwise, find the first difference, and then find the second difference if that's not the same. And then if those two aren't common, then go to the ratio. Just because the subtraction is usually easier to do than the division. All right, so how can we find a model and figure out what model to use? Here we have the owner of a framing store tracks the cost of bubble wrap for packing pictures like the one shown. How can you use the data to estimate the cost of bubble wrap for a picture with a length of 75 inches? So here, very first thing, let's look to see if it's exponential. So we have 0.1 to 0.3, so that's times 3. If we multiply by 3 again, that would be like 0.9 something. So probably not exponential, so let's not start with that. Let's start out to see if it's linear. So 0.31 minus 0.1 is 0.21. 0.62 minus 0.31 is 0.31. 1.04 minus 0.62 is 0.42. And 1.57 minus 0.04 is 0.53. So those aren't the same. Not even close. I mean, yeah, they're all less than 1, but that's not close. So let's find the second difference. 0.31 minus 0.21 is 0.1. 0.42 minus 0.31 is 0.11. 0.53 minus 0.42 is 0.11. These are the same or very close to each other. So let's try a quadratic model. So to find the model, we could use a calculator, but not everyone has calculators, or we can use Desmos, just like we did in the last one. So let's do that. The very first thing, we need to plug in the table. Remember, to make a table, you'd go to that plus option, choose table, and then it pulls up a table, and just enter the table exactly as it's written. And then in the next line, we do the regression. For the regression, we type in the equation that we want, or the form of the equation that we want. We think it's going to be quadratic, so we're going to type in a quadratic equation. Remember, quadratic, y equals ax squared plus bx plus c. Just instead of y, we use y1. To get y1, you just type y, and then hit 1, and it'll automatically do that. The little tilde thing, instead of an equal sign, is the second, and then it's the number to the left of the, or not second, shift, and then the number to the left of the 1 button, way up in that top corner below the escape. A, x1 squared plus bx1 plus c. It gives us the r squared. Remember, the closer this is to 1, the better of a fit it is. It says it equals 1. It doesn't actually equal 1, but it's so close it's rounding up to 1. When it equals 1, it's like we had an equation and we found a table from the equation. It's like that's a perfect fit. This one wasn't quite perfect. We saw that with that 0.10 instead of all the 0.11s, but it is really close. We don't need to look at the residuals, but then we get our equation. It tells us A equals 0.00148881, B equals 0.00759524, and C equals 0.002. You get to pick what kind of accuracy you want, like how many decimals do you want to use. The more you use, the more accurate you are, but you don't have to use all of them. I'm going to say y equals, or I'm going to type it f of x equals 0.001488 might as well 1x squared plus 0.00759 5x plus 0.002. All right, so there's our model. Now we want to estimate the cost of bubble wrap for a picture with length of 75 inches. We can plug 75 in, or we're already in Desmos. If we type in this equation exactly as I had it with f of x, and then do f of 75, it gives us the answer right down here. So it would cost $8.94 for a 75-inch picture. So remember, this would be the quadratic equation. If we wanted a linear regression, we would type in a linear equation. Linear is y equals ax plus b. So y1, a tilde, ax1 plus b. If we wanted exponential, exponential is y equals a times b to the x. So it would be y, a tilde, a times b to the x1. So that's how you can get each of these three things depending on what type of model you need. Now, if you're not sure, you could try a couple different models and then you can look at the graph, see which one fits better. See which r squared is better. That helps too. So now comparing models. We have a graph shows population models for 3 cities. based on data over a 5-year period. If the populations continue to increase in the same ways, when will the population of city C exceed the populations of the other two? So we have city A, which is 3.2x. This one's linear. We have city B, which is 0.25x squared. This is quadratic. And then we have city C, which is 2 times x to 2 to the x minus 5. This is exponential. So how could we tell when the population of city C will exceed the other populations? We could make a table, like a big table, like with each of them. So we'd have years for x, when x equals 1, when x equals 2, when x equals 3, when x equals 4, when x equals 5, when x equals 6. And we could just find the values for each of those just by plugging stuff in. If we do that, we'll see that city C passes city B on the 10th year, and then it passes city A on the 11th year, because exponential functions grow super fast, way faster than anything else. So we can find that. We can also look at the graphs, like a graph bigger than the one that was given. We can plug it into our calculator or Desmos and graph it to see what it'll look like. And in fact, if we do, we'll be able to see when B gets ahead of A as well. So if we extend the graph, like right here, the original one, we were just looking at, got up to 5, we were just looking at this part of the graph right there. Didn't really show us much. But we can see that in between years 9 and 10, city C passes city B, and then right about year 10, city C passes city A. In fact, it's equal at year 10. And then if we expand out year 11, 12, in between 12 and 13, B actually gets ahead of A as well. But the exponential function will keep growing faster and faster and faster, so the others won't ever catch back up to it again. It won't curve down. And so we were able to use, we made a table so we could look at the different models. We made a graph so we could look at the different models. A fun thing with doing it in Desmos is if you click on the intersection points, it'll actually give you what that point is. So you can see the x and y value. In a calculator, you have to go through a few extra steps. So this was the last section of Chapter 8. We're looking at linear, exponential, and quadratic models and comparing them. We already know how to find them all. So this is just comparing them, seeing how do you tell what it's going to be, and then looking at the different models, seeing how they change. So I will see you in class, but until then, keep working problems, keep asking questions, and as always, happy mathing.